Great. Well, welcome to the April 2023 Free Westport Astronomical Society Lecture Series. And, thanks to everybody that's joined us on Zoom tonight and the folks watching on the live stream over on our YouTube channel, where this talk and a lot of the previous Westport Astronomical Society lectures actually still reside, and you can watch them anytime you'd like. And if you like this talk, give it a thumbs up and subscribe. You can also keep up with all of our activities at the Westport Observatory, because we're on tons of socials. We're on Facebook, Twitter, Instagram, Mastodon, Tumblr, LinkedIn, and Meetup. So we've tried to cover the bases there. Our speaker tonight, Dr. Regina Caputo, is a NASA research AST in fields and particles. And originally from the southern Colorado town of Pueblo, Dr. Caputo attended the Colorado School of Mines and graduated in 2006 with a BS in engineering physics and a minor in math computer science. She picked up a PhD just across the sound in Long Island from Stony Brook University in 2011 in particle physics using data from the ATLAS experiments at CERN. Well, after graduating, she joined the ATLAS group in Germany as a postdoc researcher working on numerous data analysis, detector operations, and upgrades. And in 2014, she moved to the other side of the planet to study at the University of California, Santa Cruz, where she joined the Fermi collaboration. And this is where she started her work in the exciting world of gamma-ray astrophysics. Well, a couple of years later, with a move across the continent, she became a research scientist at the University of Maryland, working at NASA Goddard Space Flight Center in 2017. And then in 2018, Dr. Caputo was hired as a civil servant scientist at the GSFC, where she is currently the PI of AstroPix, silicon pixel detectors in space, and a mission concept submitted in 2021 MIDEX announcement of opportunity, AMEGO-X, the Swift Observatory project scientist, and the Compare Balloon project manager. So won't you please welcome to the Westport Astronomical Society Science Lecture Series, Dr. Regina Caputo. Doctor, welcome.
Oh, thank you. Thank you for the opportunity and the introduction.
It's quite the resume. It's good.
I know. I was going to say, when you list it all, I'm like, wow, that's a lot of stuff.
That's 15 minutes of the lecture right there.
And thanks, folks. We're done now. I'm sorry we have to go.
Sorry. Okay, so let's see. So I'm going to go ahead and share my screen. Let's see. Hopefully this, share. Can you guys see?
Yes.
I'll even try playing and see how that works. Can you guys see the presentation?
Yes.
Okay, awesome. So I like I said, thank you for the opportunity. I obviously love really talking about science. It's a lot of the, it's I get paid to do it. And so it's really my pleasure to share it with folks who share this kind of enthusiasm and excitement. Honestly, I get just as excited about like the pictures that you guys are taking of like these amazing galaxies. And like, gosh, when I saw images from like JWST, it was like, mind blown, right? And so, but I'm going to talk to you a little bit about something ironically that you can't see using telescopes, and that's dark matter. And so the title slide was Dark Matter Discoveries. Boy, I sure wish we discovered what it was. But I will hopefully motivate why we think that dark matter exists, tell you a few options about the candidates that we have, and really I'd like a little bit of an interactive session. So at some point I'm going to break out, and we'll have like a choose your own adventure. And so I don't know if you guys have ever used Kahoot before, but it's just a way to vote, and you guys will be voting on what kind of dark matter candidate you'd like me to go into more detail about. So just to prepare yourselves, we'll walk through it. Hopefully it'll work. If not, then I'll just pick one myself.
Great.
Okay, so without further ado, I'll be talking about dark matters, the search for the universe's missing mass. So we'll dive right in. And like I said, plus a choose your own adventure. So really the mystery of missing mass started a long time ago, almost 100 years ago, when an astronomer, Fritz Zwicky at Caltech, was actually taking photos of galaxy clusters. And so what you're looking at on the left is a figure of a photographic plate. And each one of those dots is not a star, but a galaxy. And this is the Coma cluster of galaxies. And so what he did was he looked at the way that these galaxies were moving in relation to each other. And so you could estimate the mass of this cluster in two different ways. One was just looking at the luminosity. So like how bright are these, guesstimate the number of stars, and do a calculation and guess that that's the mass of them. So that's one way. The other way was by looking at the velocity of them relative to each other, because if things behave like they do in our solar system, they follow Keplerian dynamics, then you expect the velocity to trail off as you go farther and farther from the center of mass. And what Professor Zwicky found was that there were 2 orders of magnitude difference in the answers that he got. So that's 100 times. Now, if it's off by a factor of 2, this is something astronomers are kind of used to. But like this is, a factor of 100 was too much. And he said that, okay, when you just calculate it via the stars, you get something that times 10 to the 8th times the mass of the sun. And when you do it by using that velocity dynamics, you get something like 10 to the 10th. And so this was too much. And so he said, okay, either physics is fundamentally different in different parts of the universe, which would be bad for us because like we assume it's the same everywhere. He said, or that only a small percentage of the mass comes from luminous matter, so things that you can see. And because we are, as scientists, are very creative, called the matter that we can't see dark matter. And so dunkel materia is what he called it in this paper. And so, things went on for about 40 years or so until the 70s, when Vera Rubin was doing a similar thing, but instead of looking at galaxy clusters, she just looked at individual galaxies. And, our pal Kepler came up with laws of motion. And what should happen if, these bodies behave the way that they do in the solar system is that as you go farther out from the center of a galaxy, the velocity trails off. What she found and her collaborators found, I'll go ahead and play this again, was that the velocity stays the same, regardless of where you are in the spiral arms of the galaxy. So the farther out you go, the velocity was constant. And so again, are some dynamics happening? Is something we don't understand? Or is there this halo of matter that we can't see surrounding a galaxy? And so what you can see is an illustration of the galaxy in a center that we can see, and then this halo of dark matter that's around it. And so this is, this is like I said, a big question trying to understand these galaxy rotation curves. So then this is basically how things stood, probably until about the 90s when we entered the era of precision cosmology. And so jump, again, forward 20 years. And we get an image of the cosmic microwave background. And so basically, we discovered this kind of by accident. There was a microwave antenna that was just basically listening, and there was this constant noise that was always at about the same frequency. And what this was actually an imprint from the remnants of when the universe cooled enough so that light could escape. And so this is essentially the first image you can get from the Big Bang, some 300,000 years after the Big Bang, of the universe. And what you're actually looking at, this is amazingly uniform, but there are these really small anisotropies, and that's what you're looking at, is the anisotropies. So there are certain spots that are colder and certain spots that are hotter. And if we fit this, and I'll actually explain a little bit because I think this is like super cool. If you fit this to a theory, basically the universal model of cosmology, what you get is that there is a component which is not made up of ordinary matter. That's about 25% of the universe. There's this even more mysterious thing called dark energy that's about 70% of the universe. And all the matter that we know of is about 5%. And so, you ask, okay, what the heck is this? And what's super cool is there's actually a tool that if you wanted to go and play around with the composition of the universe, you absolutely can. And so this is this website. It's called the lambda.gsfc.nasa.gov toolbox, and then there's the rest of the link. And you can actually toggle the different dark matter, regular matter, dark energy components and see what you get as an image at the end of it. So that's kind of a fun thing, you know, when you're bored. Now I'm showing you this horrible list of cosmological parameters, not because I want to go into them all in detail, but just to show you why we're so confident that there is this 25% dark matter, 70% dark energy, 5% regular matter. And so what we take is it's called the Friedmann equation. And I want to call out a couple things. There's some independent parameters that these are things that we fit for. One of them is baryonic matter. That's protons, electrons, everything that we see. There's this non-baryonic matter. This is dark matter. So this is something else. It doesn't behave in the same way that our matter does. You have these fixed parameters, which are things that you measure independently of this measurement. And then you calculate these values. So you run it through, you run these fits, and then you see what you get. And like I said, on that previous link that I sent around, the picture of lambda CDM gives you an image that looks something like this. But if we turn off the dark matter, we say there is no non-baryonic matter, it's all normal matter, you get a picture that looks something like on the right. And you think, well, that doesn't look so different. What's the deal? Well, it's because, you know, math works a little bit better than our eyes sometimes. And what you actually want to look at is the size of those blobs. And the fancy word for that is the angular power spectrum. And so if you compare the different sizes of those blobs and the numbers of those blobs, you can actually see that things are quite different if you assume dark matter, which is this LCDM, versus no dark matter, which is what's shown in green here. And what you see is that things that are on the scale of a degree in the universe size, there's many, many more of them than if there is dark matter. And so, you know, like I said, this is a fancy way to say that there's more small scale structure fluctuation. So there's more little blobby things. If there's no dark matter, you'd have really, really, really big, large structures, and we don't see them. And just to give you an idea of how well this is fit, these are fits from the Planck satellite. And you can see that, you know, the data matches really well with the prediction. And this is all of the stuff that went into getting that little slice of pie that I showed you a few slides ago. So like I said, if you don't, you know, care that much about the math and all the fitting, I thought it'd be kind of fun to dive in and show you where all this stuff comes from. Don't worry about it. The important thing, like I said, is this pie slice that we have a pretty well motivated reason for why we think there's matter that's not made up of the typical kind of matter that we get, that we have, that we can see. So in addition to the cosmic microwave background, so this is like the seeds of the universe. You start with these anisotropies and they turn into little gravitational wells, which are the seeds of large scale structure and galaxy structure. And what we could do is start with this from, you know, 300,000 years after the Big Bang, propagate forward in time using this massive simulation. They did this for the first time in the year 2000. It was called the Millennium Simulation. And what you could see is that the way that the universe forms is that there's this filamentary structure where you have these large nodes of galaxy clusters, and then they're connected through filaments, and these filaments are made up of galaxies. And like I said, we ran through these simulations since 2000. In the past 20 years, they've become way more complex. And what we see is that when we look at large swaths in cosmic time and distance from, say, like the Sloan Digital Sky Survey, we actually can observe this filamentary structure in the universe. So we could start with the cosmic microwave background, propagate it forward in time, and see similar structures to what we guess, given this lambda CDM model, where lambda CDM just says the universe is made up of 25% dark matter, 40% dark energy, and 5% regular old matter. Now, there's also instances, so completely independently of this, we observe what's called strong lensing. And matter, just like glass, can also bend light around it. And so there are these instances where it looks like light is bent around matter, but we don't see the big chunk of matter that should be there. And so what that looks like is a big chunk of matter that doesn't exist, and or that not that it doesn't exist, but we can't see it. So it's not made up of things that we can observe. And this is one instance. And one of the coolest examples of this is actually the bullet cluster. And that's what you showed on the title slide where you're talking about dark matter discoveries. And so this is a great segue because I could talk a little bit about the bullet cluster. So the bullet cluster was two colliding galaxy clusters. So you have these clusters of galaxies that are colliding with each other. And when you're looking at it in optical light, what you can see is, galaxy clusters. The galaxies are pretty diffuse. They will pass through each other. Oops. Oh dear. I went the wrong direction. That's okay. There we go. But a lot of the gas and dust that the galaxies are made up of interacts with itself, or they interact with each other, and that heats up. And so in X-rays, what you actually see is this kind of shock bow front. And so you can see the hot gas interacting with itself as it passes through. And when you try to map out where the majority of the mass is from the galaxy, you can do this gravitational lensing, like I said, and so you can map out where exactly the bulk of the matter is. And what you see is that the majority of the matter from these galaxy clusters basically pass through each other without interacting at all. And we map that out because of gravitational lensing. Whereas all of the material that makes up the galaxies was interacting kind of in the center, and you see this shock front. And so this was just, one real example where we see that, the normal matter that we can observe is interacting with itself, but actually the majority just passes through uninteracting. So this is a lot of information. And so I'm going to try to summarize it kind of quickly here. So what do we know? So we know first and foremost that dark matter is made up of stuff because we can see it gravitationally. So we know it's made up of mass. We know that mass is not made up of protons and neutrons because we get this from the cosmic microwave background. There's some other things, but mainly the cosmic microwave background. It's not made up of stuff that we're made of. We also know that it doesn't have any charge, electric charge, like an electron, for example. And we know this because that also would mess up the large scale structure. If dark matter was charged, especially at the scale of like an electron or proton, the universe would look very different than what we get. We also know that dark matter is not hot. And by not hot, I mean, it's not traveling relativistically. It's not traveling at the speed of light, because again, this would mess up the structure of the universe, and we can't have a dark matter candidate that's going to mess up the universe because we're stuck with what we have. And then finally, we know that it's stable. And this is somewhat obvious because if it weren't stable, it would have decayed and gone away. So it's at least stable on the time scale of the universe. So, 14 billion years or something like that. So we know all of these things about dark matter. But, this is one of those scenarios where, well, we know it has feathers, we know it has feet, we know it has a beak. Is it a duck? Is it a chicken? Who knows? So we're trying to figure out what exactly it is. And this is really like a very active and vibrant field of study. And like I said, one of the things that I think is really exciting. And so where do we look? Where do we start? And I'd say, broadly speaking, we break this up into 3 different kinds of categories: really light stuff, medium heavy stuff, and super heavy stuff. Light stuff you could think of as waves, wave like dark matter. And these units are a little weird. An electron volt is a unit that we use. That's the amount of energy that it takes for 1 electron, or 1 volt to move 1 electron. But you could kind of think of it as optical light has an energy of about 1 electron volt. That's a good ballpark for your pocket. So when you think about ultralight dark matter, you think of it as basically being less than the energy of a photon. Thinking particle dark matter, it's going to be somewhere like the mass of a proton, the mass of a, neutron, the mass of a carbon atom, that kind of thing. And then from there you go, well, what about things like black holes? So super heavy stuff. And so any good candidate has to satisfy all of those previous requirements, number 1. Then the next question is, okay, so we have this theory. How do we look for it? How do we determine if we're going to observe something or not? Then we say, okay, well, maybe we can observe it, but how do we actually know that we've discovered something? So how do we distinguish it from anything else? And then, the final question is, if we could check off all these things, then, how do we get to Sweden to collect our Nobel Prize? There was a really funny XKCD comic, which I'm not sure if you're familiar with XKCD, but they kind of gave a funny list of all of the different dark matter candidates, and that includes, bees and space cows and other things like that. Now, of course, because the phase space of this is so broad, that means that there's tons and tons and tons and tons of theories, and some of them are much more motivated than others. And so this is where you guys get to choose. And so I've broadly broken this up into kind of 3 options with, 1, hey, I actually don't know if I believe anything that you're saying, which is, it's fair. It's fair. And so I'm going to pull up Kahoot. So I'd like you, if you have your phone or if you have your computer, go ahead and pull up kahoot.it, and I will open up another window and tell you the game pin that you can access. And so let's see if this works. Can you see the Kahoot area now?
Yeah.
Okay, so go ahead and put in the game pin. And as you guys join, we should see people start to enter. And so we'll give folks, a minute or 2. Yeah, so it looks like people are starting to enter. So awesome. We'll give you guys maybe a minute or so to figure it out and join. This is going to be a really simple quiz. The 4 options you'll see come up, and you'll have the option of picking wave dark matter, particle dark matter, really heavy stuff, or I don't actually believe any of this. I think we probably just don't understand physics. Just to prep you.
I like this. This is a good little app. This is
yeah. Kahoot is a lot of fun. It's kind of a great way to get, people playing along.
all right. Meta's figured it out. All right.
Let's see. It looks like we're about topping out at about 17. I knew it. As soon as I said it, somebody else is going to join. We'll give it 10 more seconds and then go ahead and get started. Like I said, I think it'll be a really quick quiz. So
yeah, there's a delay on YouTube. It's about 30 or 40 seconds normally between what you see.
Oh,
on
okay.
YouTube.
Okay. If you like, I could give them a little bit more time. That's also fine.
Yeah, it's going. We're doing good.
Okay. Yeah, like I said, and like I said, no worries if if you don't make it in.
We have a quorum.
Okay. So let's see. Okay. Oh, it looks like we lost a couple. So anyway, I think we'll go ahead and get started. It sounds like we peaked at some point. So we'll get started. Okay, so let's see. This is the Dark Matter Choose Your Adventure. And it is going to start. And this is the quiz. What kind of dark matter candidates would you like to hear about? And I kind of already prefaced those. So the weakly interactive massive particles, those are the medium range ones. Axions and axion-like particles are the wave-like ones. So those are the super light ones. There's exotic options like black holes. Those are the really, really heavy ones. And then I still don't know. It's probably just gravity. That's the green. So you can choose WIMPs, light ones, which is blue, yellow ones, and green. Ooh, cool. Okay, so for those who voted, it looks like axions and axion-like particles just barely beat out weakly interacting massive particles. So depending on how much time, maybe we'll do both, but we'll definitely jump to axions. So let me go ahead
Red lost because they're WIMPs.
I picked a WIMP there, man. That's what. All right, fine.
Okay, so let's see if I could go ahead and change back to where I was sharing before. Sharing. Okay, cool. So here we are. You have chosen the wave-like dark matter, axions and axion-like particles. These are a lot of fun. In recent years, so WIMPs always were like the leading dark matter candidate. And I think that WIMPs or these axions and axion-like particles really have taken off a lot in popularity recently. And so it's not possible to talk about axions and wave-like dark matter without getting into a little bit of particle physics. And so, bear with me. And so, for those of you who are familiar a little bit with particle physics, this is the standard model of particle physics. The universe is made up of quarks, which make up things like protons. It's made up of leptons, which are made up of things like electrons and neutrinos. And then the forces that make them interact with each other. And we have photons, which is the electromagnetic force. We have gluons, which is the strong force. Think of it as gluing nuclei together. We then have W and Z bosons. These are the weak forces. They actually will change quarks, the flavor of quarks from up to down, or leptons from neutrinos to electrons. And then, of course, we have the most recently discovered one, the Higgs, and that's what gives everything mass. Now, so these are the carriers of the forces on the right and the particles that get acted on the left. Now, now the way that these particles interact with each other is through, so in particular, the strong force. So the one that binds together the nucleus, there's all these symmetries in particle physics. And lots of the symmetries, in other words, the way that the forces act on different particles, sometimes they're violated. So sometimes they act on different particles in different ways. And there's no really good reason why that happens. It just happens. And because that's what we observe. That's what we observe in nature. Now, physicists always like to think of things as having symmetry, perfect symmetry. But if there was perfect symmetry in the universe, we wouldn't exist, because there would have been equal amounts of matter and antimatter, and we would have just annihilated. So the whole reason that we exist is because symmetry is broken. And we want to understand how all of these symmetries are broken. And there were these two theoretical physicists, Pesce and Quinn, in the 70s, who proposed that the way that the strong force was broken is through adding in this new particle called an axion. And the funny story is that an axion was actually the name of like a dish soap. And they used that, it was like, they called it that to be like cleaning this problem that you had. So there's nothing deep about the name axion. It's just, it was some dish soap that they had. And so this is that new boson that I said had to exist. And so that was on the right part of the standard model that I showed. And in order to fix all the problems, it needed to be very light. So this is the wave dark matter that we wanted. So this is a very, very light particle. And what's super cool about this particle is that it connects to magnetic fields. And so it couples photons and magnetic fields to this new particle. And so this is the special way that it interacts. And of course I said, okay, so we have this idea, there's this new boson, we have this theory, it connects photons, it connects magnetic fields. So how do we look for it? So we need an experiment that can actually find it. And this is where a lot of different ideas and a lot of different complementary searches come into effect. And so the first one is just looking at astrophysics. So you look at some extreme astrophysical object, and like I said, they couple to magnetic fields. So you want something with a really strong magnetic field, because then it's likely to couple to light and oscillate into an axion and then oscillate back into light if there's a lot of magnetic field. So that's the first way, is looking at astrophysics, where we know dark matter is. Another one is to build a telescope that would look at the sun and look for axion production and signatures of axion production in the sun. And because the sun also has magnetic fields, you would say, okay, the sun produces axions, and then it would couple to this field and then produce X-rays that would be visible. And this is a helioscope, so sun observing. There's also telescopes called haloscopes, which observe the galactic, the galactic halo. And those, they're on Earth, we're in the galaxy, and they are similar because they're measuring it wherever we happen to be in the Milky Way for axion-like particles. And then there's this other super cool lab experiment called the shining a light through a wall. And so what you do is you start with a really, really bright light. You take a really, really strong magnet, you shine the light through the magnetic field, it oscillates into axions, travels through the wall, you put it through the same magnetic field, and then it turns back into light, and then you observe that light. And so these are kind of a couple different ways that we're looking for axions. The one I'm going to talk to you about, because I am an astronomer, is the astrophysical sources. And so one of these is exploding stars. So you've heard of like supernovae or core collapse supernovae, where you have a supermassive star, it explodes, tons and tons of energy is released. Well, this is the perfect laboratory to make axions, these theoretical particles. And so what you have is, say, in the little green bubble, you have photons being produced, so gamma rays. They oscillate in the magnetic fields of the galaxy, wherever it happens. This turns into an axion, and then it oscillates back, given the magnetic fields in the galaxy, into another photon. And what you would look for in this is basically wiggles in a spectrum that would normally be smooth. So instead of seeing, oh, look, here's where all the photons are, now, oh, look, we're actually missing some photons because not all of them oscillated back from axions. And the thing is that you need magnetic fields. And so you can look at core collapse supernovae, you can look in galaxy clusters. Pulsars are rapidly rotating neutron stars that have really, really strong magnetic fields. And so these are the different things that we actually look at. And I have a graduate student who looked at gamma ray bursts, and she's actually defending her thesis on Monday. Actually, and of course, we only found upper limits, or else. So we didn't find evidence of axions. But like I said, we're really just starting to scratch the surface of being sensitive enough and building telescopes that are sensitive enough to actually do these kinds of searches. And so one thing that I wanted to point out is, in particular for these helioscopes and haloscopes, we've only built prototypes of these so far. So notice these are kind of CAD models. So we're hoping to be able to actually build these telescopes instead of just a prototype that would be sensitive to actually dive into some of the axion phase space. And so that is the picture of axions. And so I can either jump to WIMPs, which were the runner-up, or I could answer some questions, or really it's up to you guys.
Well, we're not having a lot of questions come in. I mean, I would just jump into the WIMPs because that's the one that I voted on.
No, fair enough. Fair enough. Okay, cool. Well, let's jump into WIMPs then. Okay, so close runner-up. And honestly, this is where I cut my teeth on dark matter searches. So you have chosen the particle dark matter WIMPs. And really, the beauty of the theory of the WIMP is in what an amazing story it is a part of in the grander particle physics universe. So the idea of a WIMP was first proposed in the 1970s. And it starts, like most things, with the Big Bang. And so, you're thinking about thermodynamics and cosmology. And so on the left, you have time, and time is literally zero, Big Bang. And what you have is dark matter, because the universe right after the Big Bang was super hot. There was so much energy in the universe where particles were being created and destroyed, and they were flowing back and forth to each other, flowing back and forth into creation and annihilation, and everything was in equilibrium. And so this is what this means. Dark matter and normal particles, so standard model particles, that's SM, were created and being destroyed in abundance, or in an equal amount of abundance. But of course, the universe was expanding, and it was expanding rapidly. And as it was expanding, it cooled off. And so both of those directions turned off. And all you got was dark matter could annihilate and make ordinary matter, but the other direction was turned off. And this went like the mass over the temperature. And the temperature is proportional to time. And so as you can see, as we're moving forward, temperature goes down, and we're starting to lose dark matter. We're losing the abundance. Now, at some point, the universe expanded enough that dark matter couldn't annihilate anymore either. It wasn't close enough. It wasn't enough interaction, cross-section. And so that means that there were no more interactions between dark matter and the standard model. And so what you were left with was an abundance from freezing out. And this is called the relic abundance. So the amount of dark matter you had when the universe was cool enough to turn off these processes. Now, what's super cool is we see this process with current particles, right? So like this freeze out process is how we explain all the forces came to be. And so this isn't something that's like weird or kooky. This is like what we observe in other things. And based on what we know from, like I said, the cosmic microwave background, that the relic abundance of dark matter is about 26% of the total energy budget of the universe. And so that's where I put that gray dashed line. So whatever we do, we've got to get to that dashed line. And so that cross section that's going to give us that abundance has to get there. And now this is where the wonderful world of particle physics comes back in. And so we know the cross section, or the interaction probability of the weak nuclear force. And we about know what the velocity at when the universe expanded was, when things started freezing out. And so we can plot this. We can plot it and estimate what that cross-section times velocity was, and we get a number. And what that number lines up with, and this is really the WIMP miracle, is it lines up with the weak force. And so, coincidence? Maybe. Does this mean that the particle like dark matter interacts at the same level of the weak nuclear force. Like that's exactly what this means. And so this is where we get the term weakly interacting massive particles. And so for a particle that's about the mass of a proton would interact via the weak nuclear force, and you get the relic abundance of dark matter. Like I said, physics doesn't always, just work out perfectly like that. But, every once in a while. And so, so really since the 70s, people have been like, man, how do we find this particle? Like we're going to, try to figure out how to observe this thing. So like I said, lots of people call this the WIMP miracle. Maybe, if, there's the WIMP coincidence, if you want to be a little bit less strong, but this is really an amazing thing. And so, like I said, this has motivated dark matter for decades. And we have multiple different ways of trying to find it. We call it the break it, shake it, make it method. And so the first way, the break it, you take dark matter and you smash it together and you make particles that you can observe. That's indirect detection. The shake it is you have dark matter particles bump into standard model particles. So imagine you have a really big detector on Earth that's just kind of looking for particles that kind of interact with it, because we know that there's dark matter here where we are in the galaxy. And then finally, collider physics, you take, protons, like say at the LHC, smash them together and hope that you get some dark matter out of it. So you make it. So, break it, shake it, make it. And of course, all of these different methods of detection tell us different pieces of the puzzle. So if you see some signal in one form of detection, you'd hope that you would see it in another to kind of nail down, yes, for sure, this is the dark matter particle that we assume, and it's not some other particle that happened to be bumping into my detectors. And so that's why we take all these different methods. The same with axions, right? We have multiple different methods to verify what it is that we're observing, because something that's this big and important really needs multiple methods of verification. And so I talked a little bit about, there's the astrophysical methods for doing this, again with Fermi. Fermi is a gamma-ray space telescope that can do all kinds of amazing things. I'll talk a little bit more about that in a few slides. There's the direct detection, which, like I said, there are these really large detectors that are deep underground, very low noise environments, that hopes that as we're moving through the galaxy, that dark matter particles will bump into these giant detectors and we could measure that recoil. And then finally, there's, collider experiments, things like at the Large Hadron Collider, where we're hoping to smash together some particles and get dark matter out of it. And the one I'm going to focus on, again, being an astronomer, is the astrophysical methods. And so the way that we look for dark matter, because remember, this is a particle that we can't see. It doesn't make light, right? Like this is the whole point. So we have to kind of indirectly figure out how we get photons from this particle. And so like axions, you're coupling to a B field or a magnetic field. So you have photons coupling to a magnetic field oscillating into axions. This is the way that we actually would get WIMPs. And so I'm going to show an equation on the bottom, but I'm going to show pictures in the middle and then what it actually means in the top. And so what we observe, so the observed photons that we would get come from properties of the particle from particle physics. And these are things like cross-section, which just is the probability of interaction, the mass of the particle, and then the number of photons that you get out of that process. And we have theories for, what this kind of a process would look like. And that's shown, in the figure above. So this is like the spectrum that you would get in photons from dark matter annihilating with itself. But then, of course, you have to take into account the astrophysical properties. So just the density of dark matter shows. So what this is showing is the density of dark matter, say, for example, in a galaxy, as a function of the distance from the center of the galaxy. Now, say, for example, we're using like the Milky Way. These are different predictions for what the dark matter density would be, starting in the center of our galaxy and going all the way out to where we live out on the spiral arms of the Milky Way. And so to take into all of that count, we call all of those astrophysical properties, where you integrate over the density profile. And then of course, there's the distance to the source. That's just called the J factor. So a lot of complicated astrophysics, we throw it into a single letter. And then just for context, if this were the Milky Way, this is about where we live. It's about 8 kiloparsecs out from the center. Now, you'll notice that just so happens to be where all the dark matter predictions converge. And that's because that we've actually measured an upper limit on the density. And so the theory can't, grossly violate what we observe, or what we, a lack of what we observe. And so there's lots of different places that we can look. If you remember from the density profile, we expect the center of the galaxy to be the brightest in producing gamma rays. And so we've looked in the galactic center. There's also these amazing little satellite galaxies, dwarf spheroidal galaxies, that surround the Milky Way in orbit. These are very special because based on their velocity distributions, we know that they are very dark matter rich. In fact, they wouldn't be bound together if it weren't for dark matter, because there's so few visible stars. We also look for clusters of galaxies. Remember Fritz Zwickie's original coma cluster. And then there's a few other things looking at the Milky Way halo. And so far, we have not detected evidence of dark matter annihilation in any of these sources. We've so far just detected upper limits, with the exception of the galactic center. There is an excess of gamma rays that could be attributed to dark matter annihilation. However, it could also be attributable to a population of pulsars in the center of the galaxy. Now, we know that pulsars exist. We know that dark matter exists, but we don't know what it is. And so right now we're trying to follow up to see if we could really nail down if that excess of gamma rays is coming from pulsars or if it's coming from the center of the galaxy. And I think that's a very exciting and active area of research, especially in gamma ray astrophysics. And so that summarizes the WIMP. So maybe I'll go ahead and pause and see where folks are and how things are going.
Oh, this is great. We did get a question from Franco a second ago. I'll just ask it for you, Franco. But well, go ahead. You got your mic off. So,
I mean, my question is, how will you recognize it when you find it?
That's the challenge. That's the challenge. So we have to convince ourselves that what we're looking at really is a dark matter annihilation signature and not just something else that makes photons, because lots of things make photons. And so one of these is the complementarity. So say we're really convinced that what we see in the center of the galaxy is dark matter. Then we go call our collider particle physics friends and say, hey, look, we really think that we are detecting dark matter. Do you see evidence of this in LHC? Or do you see evidence of this in the direct detection, right? Like where you're putting a tank of some kind of fluid and measuring the recoil. Like, is that consistent with the particle interactions that we see? And really, to verify it, we would need some of these other methods. Alternatively, we would also need to see these signals in other things. So we need to see it in the galactic center. We need to see it in the dwarf spheroidals. We need to see it in other places, not just in one place.
What about, is there a possibility to monitor it over a long period of time, let's say 100 years, see if there is any change? Obviously, the astronomical times are extremely long, but, is there any way that maybe something changes? We're looking at gravitational lensing. I know that the times are obviously very extended.
So one of the really exciting things that I think is interesting, in particular about gravitational lensing, is they're looking at trying to use gravitational lensing signatures to narrow down the constraints, or to narrow down the potential masses for dark matter. And so if we can get higher precision measurements, which is really challenging, right? Because right now we have really amazing telescopes, but if you can get them more precise and we could map out little fluctuations of the mass, we could actually determine the composition of the lens. And so that is one really exciting, proposed idea for how we could like narrow down what kind of dark matter candidate we're looking for, or what kind of dark matter we could potentially be looking for.
Thank you.
Gravitational lensing is such a phenomenal thing. You can actually, I've seen it, with at star parties where you can see Einstein's cross, which is, I've never seen all four little quasars, because it's essentially it's one quasar behind something very dark, something very heavy in front of it, and you see four quasars around the object. I've never seen all four, but I've seen a couple of smears, and it's fascinating to see, as it's actually happening. You're seeing it right with your eyes. This light from billions of light years away is now being focused right towards you. It's quite shocking. If you've not been to a really dark sky and large aperture, you can't see it, but it's worth it to see. Another question, kind of while we're at it. So once we do find out what dark matter actually is, what are the next steps? I mean, what after that? Like check the mark off. There's more to it than that. What can you do with this kind of a discovery?
No, that's an excellent question. And the best analogy that I could think of is, back in like the 1900 when we first discovered like the electron, like that this is this particle, it carries charge, it moves around. Like, I feel like we had no idea that like electricity was imminent, right? And that created a revolution. So discovering the particles, understanding how they interacted, and then, oh man, this is something we could do with this particle. It revolutionized the world. And so, once we understand something that's this fundamental, so we have to, figure out what it is. And then based on what it is, could it be, a potential energy source? Could it be a solution to, like large scale travel in the universe? Could it be like it? Honestly, we're only limited by our imagination and probably the laws of physics, but we don't understand them all yet. So, we're learning. I think that really there's an infinite amount of possibilities as to what we could do once we understand what it is.
I always give it, when people ask me that at star parties, we have them weekly at the observatory, and the only way that I can ever really explain it to somebody, because I'm a sales guy, but it's like the scaffolding of the universe. It's what everything is kind of hung on. Everything is attached to it in some way or another.
Yep.
And
no, that's a great analogy.
Howard Nussbaum asked a question here too. You mentioned that in the early universe, the quantity dropped until a stability point was reached. Is there any theoretical coordination between the models of what it might be to a theory of how the drop in concentration in the early universe would have declined?
Could you repeat the last part of the question? Maybe I could get to the question. That's a good question, and I want to make sure that I can see.
Can you see it?
Okay, yeah. So let's see, is there any theoretical coordination between the models of what it might be? How drop in concentration, how the drop in concentration in the early universe would have declined. So it's really just a question of thermodynamics. And so, like, I guess the way to think about it is like if you have hot soup, and if it's in a small bowl and the bowl is full and there's not a big opening, it stays hot. But because the universe was expanding, and we know it was doing this through inflation, things rapidly changed. And as the volume gets bigger, it cooled off because you have this conservation of thermodynamic laws. And so, this is probably so we know how the temperature would have declined. And we know that as the temperature declined, the interaction probability, or the cross section, that's all that means. The cross section is just the probability of interaction, also declined, because as it cools, particles are moving slower. There's less energy in the particle motion. And so that's why the concentration changes. And it changes very predictably, because we know what the temperature is as a function of volume, and we can calculate what the interaction probability is as you propagate forward. I hope that answers your question. If not, I can try again.
And Lynn Flynn had asked a question too. How can gravitational imaging show things that are not gravitational? I think that we're sort of talking about that earlier, but.
Yeah, so it's all, I mean, it affects mass, and light bends around it, because remember, like, well, I don't know, but the idea of space-time, and I don't know if you've ever kind of seen this visualization of, like, in 2 dimensions, it's like a rubber mat. And if you put like a heavy ball, like a ball bearing, in that rubber mat, and the bigger the ball bearing is, the more it will dip down. And as things travel on the path, they will be arced or lensed or bent around that ball bearing. And light travels through space-time just like everything else. And so if it's on a path and there's this, heavy ball bearing nearby, its path will get bent around it. And that is how mass behaves like a lens, and it bends around it. And it actually looks like, you say, if it's a strong enough mass, or if it's a heavy enough mass, you'll see this object that was on the other side multiple times, because that's how light gets bent around this mass.
Great, I think you answered that. Oh, we got another one that just popped up in here. Let's see what it is. Oh, it's Howard Nussbaum again. I'll just read it out loud. You can answer. I think you can see it. It does, except would different types of dark matter candidates all be consistent with that same decline based upon thermodynamics? If so, and all possible candidates behave similarly? I think that was my question. I see.
So we do anticipate that there is a relic abundance of dark matter, because this is this expansion of the universe. However, this doesn't have to be the only way that we get dark matter, number one, or number two, that we get the amount of dark matter that we have today. This is really just a coincidence of, you mix the weak cross section, you mix together some known standard model quantities, and out you get, a WIMP type dark matter. Axions, for example, behave a little bit differently. You get a similar kind of freeze out, but because they're so much lighter, they actually way underproduce. But also because they're lighter, you can actually keep making them. And so there's a little bit different of a play depending on the different masses as to how you get the amount of dark matter that we get today. The other thing I want to mention is, all of the things that I've talked about, I'm assuming that dark matter is one thing. Now, it could be lots of these things. It could be dark matter, it could be WIMPs, it could be axions and black holes all mixed together. Like, the standard model is really diverse in particles. There's, 4 times 3, 12 different particles, 5 different force carriers. Like, there's no reason to think that there isn't an entire dark sector of particles for us to discover. And they could be all of these different things. And, but we have to start somewhere. And so we start looking in, okay, what is the easiest, most obvious thing that we can check for? And, this kind of WIMP thing is obvious, and the axion thing is obvious. And we've also looked for black holes. And as it turns out, you need like ridiculous numbers of black holes to account for all of the dark matter. And so that, as being all of the dark matter candidate, has actually been ruled out just for that reason, because you'd need like black holes everywhere.
What are some of the next ways that we plan to detect this? What are the next steps? I know that Rubin's being built, getting done. What else can we expect to see to detect this? I think that they've got a dark matter detector. I grew up in South Dakota, so I know they have one out in out in the hills, in the Black Hills of South Dakota. What else? What are the next things that we can detect this, and what can we see being built?
Yeah, no, that's an excellent question. And so I think that like we're really starting to scratch the surface of these dark matter candidates. And like we've for the most part, I think, ruled out the most boring vanilla kind of WIMP, and we've ruled out the most boring vanilla kind of axion. But all that means is that the universe is much more interesting and rich than we could estimate the first time on our first guess, which that's fine. And so we're coming up, like I said, with some different ways of looking for dark matter. Like, I had mentioned on the wave-like dark matter side, getting, helioscopes and haloscopes online, looking more deeply at gamma-ray bursts and these very extreme astrophysical accelerators. So just more telescope time and trying to map out the magnetic fields and where they are to find the most probability of where we'd find these. Using observatories like Vera Rubin, which will really map out the large scale structure and give us more of a handle on gravitational lensing. That's also really important. So when that comes online, that's going to be really big. And then thinking about, okay, once we know a little bit more, what kind of telescope could we design to really drill down? Like I had mentioned, something that's really super stable that could map out really well, say, the mass distribution in the bullet cluster. And that could tell us, oh, maybe it's not this whole giant range of masses that we can look for. It's instead this more narrow range, things like this.
Well, I don't see any other questions coming in.
I have one.
Oh, yeah, go, Shannon.
I have one. I was just kind of waiting. With both of these candidates, axions and WIMPs, you mentioned on both of them that the candidate interacts with magnetic fields in some way to produce photons. Can you elaborate on that a little bit? What's going on there?
Sure. And so I'll go ahead and let's see if I can pull up do this. We'll go here. Yeah. And so the electromagnetic field it's a similar, so the reason we call it electromagnetic is because electricity and magnetism interact in a very similar way. And the force carrier for this is the photon. And so photons carry magnetic fields, they interact with things that have charge. And what's super cool about axions is they connect together interactions of magnetic fields and light. And so what happens is you get an axion, which is just a particle, when it gets into a really large magnetic field. And the reason I say large is only because it increases the probability of interaction. If there's an infinitely large small magnetic field versus a small, really strong magnetic field, it's the same kind of probability we're talking about. And so axions, so they interact with this magnetic field, and then they can produce photons from that. So basically they oscillate into a photon, or vice versa. You have axions and they oscillate into a photon when they're interacting in a magnetic field. And a way to kind of think of this is, I'm not sure if you're familiar with, say, a photon. It can interact with a nucleus and pair produce into an electron-positron pair. And this is it's kind of a similar process where you say, okay, that photon, it interacted with the nucleus and then underwent a process that changed it into an electron and positron. In the same way that, an axion can be traveling, it interacts with the magnetic field and then oscillates into a photon. And
the reason I'm asking this and what I was wondering is, if a strong magnetic field, if axions, for example, interact in a strong magnetic field to produce photons, wouldn't something like a neutron star be optically bright? since it's producing
Exactly.
photons.
Yeah, exactly. No. That's the question. And the whole, it would be if it coupled in such a way that produced optical photons.
Right.
And so the energy of the photon depends on the coupling to that magnetic field. And so that's where it gets a little bit tricky, because say, for example, we were looking in gamma rays, and that probes a very specific part of the parameter space, because we're saying, okay, we want axions to oscillate into gamma rays, because that's what we're going to observe, say, instead of optical photons. And so these are the couplings to that magnetic field that we are sensitive to. If you're looking, say, for example, in your pulsar, and you're saying, oh, we don't see any optical photons, that must mean that it doesn't couple in these particular ranges. So this particular probability of interacting with the B field is highly unlikely. And so it just allows us to put different constraints on it.
All right, thank you.
Sure.
Any other questions? Anything from the panel? Well, I have one last one. Obviously, we went through your resume a little bit earlier, but how did you get? I mean, what sparked you into going into this line of field? What got you into just the science of this?
So it's funny, because I feel like there's some aspect of like a random walk and some aspect of like I was always kind of nerdy.
All of us are that. Anybody in this group is going to be a little nerdy.
Yeah. So I remember when, so I was really lucky when I was an undergraduate and I was studying. So I was always interested in science, and I didn't really know what science I wanted to do. In high school, I really liked chemistry. And then when I went to college and I studied a little bit more about chemistry, I was like, oh, I actually really like the more fundamental parts of chemistry. So like how particles interact. And that's what got me into physics, is I was like, man, the particles are cool. Who doesn't want to like learn more about that? And when I was in college, so I decided to major in physics. I went to a colloquium given by Leon Letterman, who received a Nobel Prize. So we were really lucky. He was like on tour doing outreach, talking to undergraduates. And he won a Nobel Prize for neutrino oscillations and for measuring neutrinos. And at the end of his talk, he took questions, and I was like, this is the coolest thing I've ever heard. How do I do what you do? And instead of like scoffing at it, he was like, you should get a summer internship at Fermi Lab. And he was like, here's this program for undergraduates. You should do it. And I was like, okay. And so I applied to this program and I got in, and I actually did a summer internship at Fermi Lab on a dark matter experiment that was in a mine in Minnesota. So one of the competitors of the ones in South Dakota. Friendly competition. Not
as good.
Yeah, I know. LZ has a stronger limit than CDMS. But that was kind of history, right? So then, I went on to graduate school to study particle physics. And then, later on, I decided I wanted to do particles in space. And so then I became an astronomer and an astrophysicist. And, that's kind of how I ended up doing things and, where I am.
Oh, I love it. What a great talk tonight. So lively, so interesting. And I love your laugh.
Thank you.
It makes it great. Well, ladies and gentlemen, there you have our speaker tonight, Dr. Regina Caputo. And again, this will be up on YouTube here in the next couple of days after we snip out the beginning of it. And so you can watch all of those programs. And don't forget, coming up on May 16th, live back in the classroom for the next couple of talks, we're going to have Scott Hughes from MIT. He's going to be talking again, Einstein's Ears, the new astronomy of gravitational waves. So that is next month. So what a great night. And thanks everybody for joining us. I hope to all see you next month. Well, thank you. See you. Thanks, Doc.